coming. It's nice out, but it is a little chilly. So we'll today recap what I talked about regarding the factors of safety. And I have a lot of examples today, and I'm going to progressively go towards failure analysis. We're going to talk about welding, but other issues that, other than joining, that will lead to failure. And when we have a failure, the type of approach that we use in practice to learn from it. It's surprising how there are lessons to be learned by doing the investigation, looking at broken pieces in details. A lot of times the idea is explain why it failed, and then depending on the answer, there are different ways to mediate it, so in the future these issues don't come up again. It will be just an overview. Obviously, failure analysis is something that is slightly different from one industry to another, but the base principles are the same. If something goes wrong and you're one of the first one to be called to find out what happened, you have to be careful with what you do. You can't just take the broken piece and melt it to figure out, what's the melting point. You have to think that there will be other people also interested to learn from it. So preservation of evidence is very important, which means that in terms of what we talk about in the class, I'm limited to the things that I was able to hold on to after a while. Last fall, I worked on an elevator on a campus very close to here, but they didn't want me to have the pieces at the end of the day. It's same with a ladder and those sort of things. There's just there's too much contingency. They don't necessarily want me to explain all the details in class anyway. But I have clearly enough. I'm giving you, in terms of failure analysis, an abbreviated version of what I gave on the other class on fracture fatigue. So it should be interesting. I have this big piece here. So one of the things we'll do today is figure out what happened here in terms of crack initiation, crack growth, and all that stuff. I learned it's good for me to have a big piece so you can actually see without all getting too close. So we'll see how that goes. If you remember from yesterday, I said we tried to evaluate the load applies. We can call it the demand. Here they call it P for a probability of failure, and then R for the reliability. You come to that demand, it's three-dimensional. So if you come to, here's my demand. That's the load, it's the environment, the temperature. It has a lot of parameters associated with it. And then you either have the resistance, or I like to call it the capacity. Maybe resistance is a good term because it does involve taking into account, do I have chemicals? Do I have chlorides here that will cause slow cracking? Or do I have any hydrogen that will cause embrittlement? And all those parameters influence the capacity or the resistance of the material to a given application. So I make my best estimate. This is where I think I am. And then depending how I do this, if I'm using, as I mentioned, in terms of working stress, I take the pressure in a steam system, nominal pressure, 200 psi. And then I say, well, the capacity, normally my material will be able to take 1,000 psi, so my factor of safety is 5. But again, in all steam system, there will be some water hammer, and these multiply that steam pressure. It's essentially, if you have enough condensate that it fills the line, all of a sudden, you have slugs of water running into the pipe, and that's what's creating the noise. If you have just enough water that is still in airflow, there's no dynamic. But when you start filling that section of pipe with condensate because there was too much cooling, it has to do with the external environment. If you're stopping the system, it creates a lot of condensation, and your drainage is not fast enough to get rid of it, you start the system over again, and that's where the disasters happen. So the drainage, they call it drip leg. I worked on a project to supply a lot of government buildings in DC just by the White House, and it's a very old system. And the reason is, same as everything else, no one wants to deal with this disruption of putting a new system in. It's under the streets by the White House. Digging out there would be, a big project, very, very expensive, very disturbing. So to the extent that they can continue to use the system, they will. They'll do inspection and make some modifications, even though the maintenance is more expensive than just putting new pipes in. It's not really an option. But what I wanted to say about the condensate is, say you have a street that's going down. So say it's going that way. You have to think about your supply. So say if it's, we're talking about the steam supply going this way, you would want to break it down and then have these legs every once in a while that will collect the liquid. So you have the steam going down the street, and the liquid is getting trapped in these drip legs, and then you turn it into the condensate line. You just turn it over to the other system. You always have supply and return on these systems. The condensate is obviously a smaller pipe, but the idea is, you can see if I'm shutting down the system, I get a lot of condensate. My slope is less than what we would do nowadays just because it's an old system. And then all of a sudden, I have the full section here full of water. And if there's a pressure differential there, it starts to go. And it's very, very dynamic. It hits a corner, and that's what creates a lot of undue loads on the system. So if you have welds there, that's why you need a factor of safety of 5. Because we're not talking about something that will happen 10,000 times. If you remember from yesterday, those graphs at 10,000 cycle, it's still sort of okay. You have a good capacity. So we're not talking about a million times that this event will happen, but maybe thousands of times. And that's why what we call the factor of safety of 5 between the pressure that is normally in the pipe as opposed to the capacity of the pipe for hydrostatic pressure. When you include all the dynamic, we're getting closer to that 20% margin because there will be welds in the system. I mean, it's all steel, needs to be put together in an efficient way. So all these factors just broaden here my estimate. When I said, oh, I know I'm here in the demand, for example, but in reality, the demand sometime will be less, but sometime will be a lot larger. I mean, it even keeps going here. So that's why, if you look at this here, it's very broad, and that's the reality. And it's the reason why we have these codes and standards to give us some ways to consistently design systems. So working stress, factor of safety of 5, we should be okay for a water hammer. It's a lot easier to do it that way than try to do fluid flow analysis, trying to figure out what's going to be the stress in the last joint before the elbow on such a system. It's just such a complex system that you would not want to do the detailed analysis of the demand. You just make an estimate, and then you take a factor of safety. So this probability of failure, the failure boundary that we talked about, I mentioned that it will depend on the application. There are applications where you're okay to deal with a certain probability of failure. And I mentioned also to you about the usage. The longer you use something, the more likely it is to fail, even though the instantaneous probability of failure is low. We talk about 10 to the minus 4 here. Say if that's per day, when you start adding up and you're at 25 years, one of the things with plumbing systems, they can be designed for 25 or 50 years or 15, depending on what exactly the application is. there's a lot of unknown. And that's why your effective factor of safety goes down as you use more and more. As you use more and more, these lower probabilities still matter. And if you see right here, if I start with 1.5 and I just keep reducing the probability, I'm getting below 1, I'm going to have a failure. And it could be for an application it's acceptable, it could be that it's not acceptable. So when we're talking about service history of a new product, plastic pipes, for example, polyethylene pipes used for oil and gas transport underground, it took a long time from the prototype to realize what were going to be the problems with that system. Creep is a problem. The pipe just continued to expand and expand because polyethylene creeps at ambient temperature. Is it acceptable or no? Well, people had to try it. So they've done a few pilot studies very, very long term and realize, oh, well, we have to worry about this contaminant, we have to worry about the joining, we have to do this. And then by the time that was done, it took a long, long time. You could invent the best pipe ever and in your lifetime not be able to put it in service. And that's what happens a lot in aerospace. Even if it's a great change, a new alloy, it can take 5 to 10 years to get it into a commercial aircraft because of all the regulation, all the history that you need to build on prototypes. Airbus has been better in terms of innovation, material innovation, and Boeing, for example. And they had to fly, before they started using some composite in the fuselage, they had to fly it for years and years on just small sections that were being inspected very often before they started saying, okay, well, yes, we can move into production of this specific section because we've tested it. We have all the history, the effect of moisture. When you start using composite, moisture becomes really important. So it takes a long time before you can say, well, it worked for the first year or it worked for a test flight. Okay, well, will it work in a normal service for a 20-year life is what the question becomes. So I emphasized last time it's difficult to start a design from scratch. So everything that we talked, and I brought the book on factors of safety if you're interested. It is really a lot of equations. And I've only used sort of what I thought would be something you'll remember, but there is a lot of theory to go backward, to look at it more from a statistical point of view as opposed to the practical point of view. We're insisting a little bit more on the practical point of view, obviously, in this class. But if you forget about exactly how to do it and you just think about the likelihood again, the more you do a detailed analysis, the more you narrow down this range here in terms of what is going to be the demand, and you narrow the capacity, you say, well, I have all these specifications, I have these inspection procedures, I'll have a lot of quality control, I can narrow this, and that's how you can avoid that, reaching that failure boundary. So if this was here, the risk region, that's how you try to avoid it, by reducing the envelope. The broader the envelope, if you build something and you don't tell people, well, you can only use it for a certain load, there will always be a failure, essentially, unless the example I'm giving sometimes is a trailer. If you build a trailer and it's so big that you fill it with dirt, everything will break, the whole axle, the wheel, all of it. Well, you should tell people, you should have a sign, well, this is the only thing you can put in there. Say it's 4,000 pounds, you say 4,000 pounds. Is it acceptable? Well, I think it is, because if someone really makes a mistake, okay, so what? He's busting the suspension. Okay, there's nothing going on. In an elevator, it's different. We had elevators for cars in Boston that people started using for construction. Well, it was very clear. It's a car elevator. If you start coming in with concrete debris from demolition, yeah, you can overload the elevator. But for passengers, if you go into a building, supposed to be able to fill it all up, okay? That it's designed so you can't really overload it. But there are a lot of more industrial, when you go to industrial application or special application, there's a big difference between the weight of a car and a forklift with, pallets of very heavy materials on it. If every car elevator was supposed to handle construction load, nobody would buy a car elevator. That's where the problem is. So if I'm a car elevator designer, what I would like to do is make my system so it's not going to all fall down. I'll have damage if the load is exceeded, but it's not a risk of the cables breaking, for example. So I get damage to the guides, and they know they got to replace because there was an overload, but it's not like the whole cart's falling down. So in terms of reaching the critical capacity to get an elevator to go down, even if it's a car elevator, it's a situation you still want to avoid. So the consequences of the failure really, really matters. This semester was a lot about joining. You guys learned a lot about welding metallurgy for steel, for stainless steel, aluminum. It will be very helpful to you if you try to build just about anything. You want to think in mind, given the example of a trailer, I built my own trailer, and I started with steel for the main structure, and then I went to aluminum for the cover and everything. So I can walk in it and all of that. And seriously, I wish I did it all aluminum. You know why? Joining. To join my main frame to the upper section, now I have a lot of fasteners to deal with, and they're hard to put in. You have to put a lot of holes and line things up, and eventually if you don't put enough now, you get to do some replacement. It's a safe system if I have 60 fasteners tying the roof to the base, and I'm starting to have a few failures. Oh, well, my fasteners are not big enough. But if I welded everything, it would never have become a question. So it's just part of trying to optimize. Obviously, steel is very strong. It doesn't have as much fatigue issues, so it's a good choice for the primary frame. It's way too heavy to build walls and a roof. So it's kind of a compromise. More trouble with joining, because I decided to use, for the two parts of the structure, dissimilar materials. For buildings, I've looked at probably 20 roof collapse, but at some point in time I summarized here 7 of them, and in 6 of the cases out of 8, the welds were the cause of the problem. And that's a little bit related to what I said yesterday, where they think about size of members. So if I have just a very simple roof joist with a top chord, lower chord, and then I have this first diagonal. This is the diagonal that's going to carry the most tension each side. And then I got some simple support. This is the simplest structure I can come up with. And then I have a bunch of little diagonal that if I'm failing a joint here, it should be all right. If I'm failing 2 of them, then I'm starting to lose stability. I could have sagging of the joist, or I could have a partial collapse, depending on what it is. So what a lot of joist manufacturers do is they make that first connection in a different way than they do the others. If you remember the flare bevel design that I've talked about quite a bit, they could have this round bar going around, and here they put 2 flat bar that you weld just on the side of the tube. These are easy fillet welds to do. There's no doubt that they'll reach the capacity you need, and it allows you to deal with some imperfection here in the core. The idea of these round bars is just so quick to make. They bend it back and forth just like I showed, and put it in, weld it, and it's over, as opposed to having multiple pieces. It's very, very efficient. Yet, if you don't control the conditions, then you have a risk of a failure. The 2 cases that had to do with the members, one of them was really sad in terms of engineering. what happened was it was a prefabricated hangar for aircrafts, and they had two sections right in the middle of the truss for the roof. So this is the whole building going like this. They had a big truss going each way, and they had these cords. This is exactly how it was. So say I make it this way. This is the lower cord, and essentially these were two different sections. You take this side, you take this side, you put them together, and you have a bolt going around here to connect them together. Now it turns out this plate was only half the thickness of the cord, and the distance was too big, so they started deforming here the end flange, and it started opening up the welds, and it had nothing to do with the weld himself. I mean, I got called in because I was the welding guy. And I just said, don't expect anything more from the weld. If you tear it, if you just pry it open, yeah, it will fail. So the initiation was the bending of this end flange, but it was a decision of the designer. Somehow didn't just run the calculation. It was very unfortunate. They had a big loss. There was a lot of private jets, and everybody was all wanting to go back to whoever made that decision, which sometimes actually is somebody that is very hard to really blame, because they don't know everything. If you're just a typical engineer and this is a new design, say, all right, I need a big cord and I'm going to put it together, and you look at something that's been made already, not considering all the significance of this distance. It happens a lot when I work for manufacturers. You realize they've been doing it a certain way, then you start asking why. There's a reason. Somebody inside the company thought about it, but it's not necessarily the guy who's working on the product at this point. So when people start trying to make changes, the first question I ask, well, you just make sure you know why everything is made the way it is right now, because otherwise you just lose that knowledge and experience. I was talking about welding before I got a little bit too much into the members here. So these are just angles. The crib angles here is used a lot for roofs where each chord is two angles. So the way it looks like is you have an angle here. I'm looking at the lower chord. You have another angle there. These are very cheap components per pound to make. It's a lot less expensive than buying tubes that needs to be extruded and processed and drawn in a certain way. And then they put the diagonal in between. So say I have another angle coming down over, say, all the way to here. It's an angle at the diagonal, so I have another angle, and the way they do it, if you start with a 90-degree angle, they bend it a little bit, they flatten it, and that's what you see right here. So an angle, another angle, and here these are the flattened diagonal. These welds are extremely difficult to make. We were talking about the flare bubble detail. Now you have a very, very hard access. So it's hard to make them reliable. The good news is they're doing both sides. Okay, so if one of them is incorrect, the other will be able to take all the load. But it's confined, completely confined. You have to come from underneath to do the welding on this leg here and on this leg. It's a very hard access. Yet it's the cheapest way to make them. So fortunately, in terms of inspection, it's not too hard with a trained eye to determine here if you have fusion or not. The only problem is there's so much fabrication that how much are you going to have an independent inspector come and look at these? Now, again, when they do this, most of the time it's only for the center portion of the joist. You get to the end diagonals, it's a different detail that is more reliable. So that's really the difference. This detail here is very different. This was all tubes. So you have a tube cord. That's what we're looking at down here in the tube diagonal. It was cut on an angle. That's how it's done at Logan Airport. You look at all these tubes and they have all these welds. It looks great. It's just not exactly what is going to give you the maximum strength. So I don't know on your handout if you see clearly, but what I'm looking at here is rusty steel that is exactly the profile of the original tube. So the only place that I had fusion here, that I melted the cord, is this little piece in the corner here, and then I have another little piece there, maybe a little piece here. Yes?
Turn down the amperage on the motor so that you heat it up slower with that action.
Yes, it just takes longer. Exactly. Yeah, it is always the option of going slower and putting more heat. So you supply more heat and you provide less filler, essentially. So at the extreme, if you think about TIG welding again, you don't provide metal. You just wait for the two metals that are already there to fuse. You never have that problem. I mean, it's because everything needs to be really, really hot on both sides. If you go really fast, you can just caulk, essentially put metal on the surface that is not bonded because you didn't take the time to melt the base material. Yes, it's a very good question. Thank you. Anything else on welding? Because we're close to the end of the session. And it's great that those things come up, because in any welding procedure, that's what I worry about the most, that a guy is going to try to go too fast and he's not going to be able to melt. And what I've been trying to do sometime for a critical application is select the welding process that they can't go too fast. With a stick electrode, it's a little harder not to melt. It can still be done, and if you tell them a certain polarity, it's even harder. If you provide more heat to the base metal, the electrode's not going to go away and you'll be able to do it. Now, there's the other extreme. These are relatively thin wall, 1/8 of an inch. So if you come in straight polarity with a big electrode here, you can have burn through. And it doesn't look good. People don't like it. You have other issues. But in general, the tendency is for things to be done too fast. Professor Eager mentioned about gusset plates. I'm sure some of you know, but I want to make sure, so I built this morning. It's a tube. I made a notch in it. So all you do is you put it against, that's the gusset plate, it's a flat plate, and then you come and weld. The advantage of doing this, so it's just a linear joint. If I put the weld here and here, it's going to be loaded in shear when I'm trying to pull out. It's a much better way to apply a load on a weld than in tension. In terms of all these, even the AWS will give you maybe a factor of 2 in fatigue strength for pulling this way as opposed to coming here and trying to weld the end. The other reason, I mean, it is a hollow tube, so if you try to weld the end, now you have to put a plate, and it is more complicated. But when we talk about gusset plate, that's what is going on. It doesn't mean it has to be welding. You can put bolts here. If it's a flat member, you can have rivets. On the main bridge structure, you can have a pattern of 40 bolts or rivet, and that's how you make your connection. It's got a lot of redundancy, yet if you start having fatigue on the first bolt hole at the bottom and it start cracking, it will continue. That's the problem with cracks, is when they start, they typically don't end. They continue. What Professor Eager mentioned that was really relevant, and it will come up in one of our examples, is not to weld the end here. So if I have the notch and I'm starting to weld this little end, now that area is loaded in tension. It's really stiff, but if I start applying cyclic load, I'll start a crack right there. And then the crack is definitely, the way for a crack here to go around this way will take a lot of energy because it's in shear, but it just starts to go and break the tube. And we're going to go through an example of that. This is an example with the gusset. So the idea with the gusset is to be able to put different members. They're not that many. I worked on a project. We were building these dishes for radio telescopes. It's to say it's 120 feet in diameter, and the idea is to focus all the radiation coming from the space into a single detector. So you need a very, very precise shape to condense and focus all the information. So it's facing up and it's reflecting into a detector that is in the middle. They had sometimes nodes. So if I call this a node, they had up to 10 different tubes getting into a node. So the only way to practically do it, and this had to resist fatigue because they will change the angle, go around, and resist the wind and all that. So the only practical way is to have a bunch of plates at different angles welded together, and then you come and from that node you attach the different tubes with this welded joints. If you try to do it with bolt, it'll take forever. But with welding, it's very flexible. I don't have to try to line everything up. I put the tube, a little bit this way, a little bit this way, and it works. That's the great thing of it. And in a lot of buildings, they do that for bracing connections. So they do the whole building. They try to put everything square. There's always going to be some deviation. So when they come with the diagonal, they love to be able to weld it because they don't need an alignment in the holes. It's very simple, but yet it's how it works. I'm presenting here a relatively general failure investigation. This is something I presented before to civil and all sorts of engineers. They love seeing the bridge and the overall structure. So they were building, that was back about 4 years ago, a bypass bridge for the Hoover Dam. So this is off Las Vegas. You used to only have to go through the dam. That was the only way from Nevada to Arizona. And they built that bypass bridge here, which is a prefabricated concrete arch. Each segment here weighs about 50 tons. It's relatively small. And they put them all together. You can see that these are temporary tie-back to put everything together. We were working for the contractor here, so we had some stories about them when they reached the middle, making that segment. Everybody was worried about it. Everybody was, wanting to know what's going to happen because the last segment was cast in place. There was no way coming from both ends that you'll arrive exactly to what you wanted. So it was the very end of a very elaborate process, and yet it was the most difficult section to put together. Now it's only loaded in compression right in the middle. So it didn't need that much reinforcement of anything, but yes, casting in place was a big adventure. For this project, each segment, these 50-ton segments, is all, was it post-tension or pre-stress? I can't remember, but they had the concrete fabricator build a plant next to the project to make each segment as opposed to trucking it. So when we talk about the cost of material is really low, you bring the raw material, then they were building it segment by segment. The idea is to use the steel in tension and make sure that most of the concrete is in compression. What happened, the reason we got involved is they had this crane going all the way across the canyon. So from these towers to these towers, it's half a mile. And they were using a trolley to bring each segment of concrete in there. The problem was in a windstorm, the towers collapsed. So if you look, you can see it a little bit better. It's two towers, and you can probably see, is it clear from here? Yeah. They are skewed. They move because you want to be able to position exactly where you put the blocks. So you have two towers, and they both lean this way. The backstay cable, we don't see it in the, we saw it. These backstay cable were fixed length, but then they had a lot of pulley system to be able to rock it back and forth to cover maybe 50. It was more than 50, about 100 feet of width for the main structure. The problem was, again, the crane collapsed, and they wanted to know why. It was supposed to be able to resist a gust wind speed of, I believe, 50 miles per hour, and it's exactly what they had on the day it came down. Nobody got hurt. That was great for that, but you can see that on a project like this, they ended up about a year behind. And they had a lot of obligation to the state to finish on time. They had to negotiate, try to explain what happened. And that was the only crane in the world they could use. at the time that they started this project. To cover a half a mile with the loads that they were looking at, it was one crane. And as it turned out, it was a crane that had not been used for a while, so it was sitting in some yard and had corrosion. This is not necessarily something, if you ask for a crane, they won't tell you, oh yeah, the one we have is all rusty. They say, yeah, we'll provide you a crane. So they refurbished it, but it turns out the refurbishing was not done correctly. This is how, if you look at this detail, which one is it? Yeah, we're looking at this area here. This is the base where it was located. And that specific tower, there were 4 of them, right? 2 on each side. That specific tower tumbled on itself. So you have, this is the bottom going that way. It was completely separated in the middle. So what was there ended up here. And then it's all crumbled and going around with a bunch of cables. They had probably 600 damage, at least 600 damage connection. I mean, there were 200 diagonal per tower, and what we did back then is look at all 4 towers in general and see, which one probably pulled on which one and how the cables were laid out. There were some cables, there's one tower under the other. Well, there's one that came down first. Yes. Yes, all 4 of them. And when we went to the site the first week, there were approximately 20 engineers, and everybody was all over the place. Nobody had a clue where it all started among all 4 because there was no eyewitness. It happened during the storm. There were a few people. It just said it just happened all at once. Well, no, that's not possible. You had to initiate somewhere and then propagate in some other ways. So there were broken cables, broken anchors for the cables to the ground, and a lot of bending and failure of joints in the towers themselves. So what we